Hello, welcome back. In this video, we are going to finish section 6.1. In the beginning of section 6.1, we reviewed some power series skills. So we found the radius of convergence, we talked about the difference between a series converging and diverging, we looked at how to put multiple series together by changing the indices and changing some of the exponents, we looked at how to add, subtract, multiply, divide series. All those skills now are going to be put together with the second half of the section. Second half of the section, we are going to use power series to find solutions of differential equations. So we're going to look at differential equations and we're going to solve them using power series. So then our solution will be a power series. So for example, we are going to consider the differential equation dy dx subtract 2xy equals 0. Now, first I want to solve this traditionally, the way we've done before, and then we'll talk about using a power series. So if we're going to solve this, you should notice that this is separable. So we get dy dx on one side, move 2xy over to the other side, get your y's together, your x's together, so I'm going to divide by y, and then I get 2x dx. Integrate, so we get the natural log of y is equal to x squared plus c. So then if we look for an explicit solution, we get y is equal to e to the power x squared plus c, which tells us that y equals e to the x squared is a solution. That's one solution. That's the case when c is 0. Now yesterday we reviewed some of the most common Maclaurin or Taylor series. We looked at cosine, sine, e to the x. I told you those are the three ones you really need to know. So this solution can also be expressed as a power series. So using a Maclaurin series, our solution can be expressed as y is equal to the sum from n equals 0 to infinity. Normally it would be x to the n, but since we have x squared, it's x to the 2n over n factorial. So what we're going to be doing today is we're going to be starting with this differential equation, but we're going to use power series to solve the differential equation. And we're going to end up with a solution like this, which we then sometimes will know what function that is, and sometimes we won't. So for the first example, example 5, we're going to approach that same differential equation from above, this time using power series. So we are going to find a solution of dy dx minus 2xy equals 0 in the form of a power series in x. Okay, so I'm always going to tell you that I want the solution as a power series. You're not going to need to know when to do that, I'll tell you. Okay, so here's the basic idea. First, we need to assume that a solution does exist. In the form of a power series. So in the form y is equal to the sum from n equals 0 to infinity of some constant x to the n. So this c of n just means that the constant changes for each value of n. Okay, so the basic idea is we're going to have to substitute this into our differential equation. X is just x, y is this power series. We're also going to need dy dx though. So we're going to have to take the derivative. This will be the sum from n equals 0 to infinity. Bring down the n, and then we have x to the power n minus 1. Okay, one thing I want us to notice though is if we plug in 0, we're going to get a term of 0. So a lot of times what we'll do then is we'll actually start at 1. Nothing changes it, just that lower bound. And that's because we aren't interested in that first term of 0. Okay, so now what we're going to do is we need to substitute this back into the differential equation. So we have our dy dx minus 2xy is equal to 0. So we get the sum from n equals 1 to infinity of n c to the n x to the n minus 1 minus 2x times y. So that's the sum from n equals 0 to infinity, c to the n, x to the n. Okay, so this is where we're going to start using some skills that we did yesterday. This, we need to be one term together, so we're going to put that 2x into the summation. So the first summation stays the same. So I now have 2c to the n x to the n plus 1, because I moved that x in. Okay, ultimately what we want to do is we want to get one summation together. So we need to figure out a way to combine these two summations. First thing that we're going to have to do is we're going to have to look at what term they start with. So if I plug in 1 here, this first summation starts with x to the 0 power. If I plug 0 into this term, into the second summation, we see that that second summation starts with x to the first. Now, we're not going to be able to combine those if they don't start with the same power or the same exponent. There's no way for this sum to all of a sudden start with x to the 0. This sum, though, if we take out the first term, so if we take out the x to the 0, we're then going to have x to the 1 first and so on. So what we're going to do is we're going to take out that first term. So if I plug in 1 to this first summation, I get 1 times c of 1, x to the 0. Now the summation starts at 2, because I took the first term out. Okay, so this is just the same as that term. All I did was took out the first term. Okay, so now if we check, if we plug in 2, we have x to the first. If we plug in 0, we have x to the first. So that's good. But we start at n equals 2 and n equals 0. So here's what you're going to need to do next, is we need to get these to start with the same value. So instead of having that power of n minus 1, we're going to let it be k. So we want that to be x to the k. K is just some arbitrary term. Here, I'm going to call k to be n plus 1. So all I'm doing is I'm just changing the indices a little bit. I'm not changing the sum at all. And you're going to see why I do that in a minute. This first term just becomes c1. Okay, so here, if my k is equal to n minus 1, if I plug in n equals 2, I start from k equals 1 to infinity. My n then, if I add 1, so that n, I add 1, that'll be k plus 1, c to the k plus 1, x to the k. So then this second summation, if I plug in n equals 0, I go from k equals 1 to infinity. N then is k minus 1, so I have 2c to the k minus 1, x to the k. Okay, so now this is looking a lot more helpful. Both of my summations are in terms of k, and then they have the same indices, same starting and ending points, so we can put those together. So what this gives us then is that differential equation dy dx minus 2xy, that becomes c1, add the summation from k equals 1 to infinity of k plus 1, c to the k plus 1, minus 2c to the k minus 1. I factor out x to the k. And if we remember, the differential equation is set equal to 0. Okay, if this is set equal to 0, we need all of our terms to be 0. So we're going to set this equal to 0. What that means is that this term is equal to 0, and it means that that term is also equal to 0. Okay, so here's what that gives us. We know that c1 is equal to 0. we also know that k plus 1, c to the k plus 1, minus 2c to the k minus 1 is equal to 0. For k is 1, 2, 3, and so on. This, I'm going to solve for c of the k plus 1. When I do, I get 2c k minus 1 over k plus 1. Now this, if you remember, when you've done power series or series at all in the past, this is called a recurrence relation. So it's relating one term to previous terms. Okay, so then here's what we're going to do. We're going to start plugging in values of k and see what we get. So if I plug in k equals 1, if I plug in 1 here, I get c2 is equal to 2c0 over 2, which is just c of 0. So I get c2 is equal to c0. If I plug in k equals 2, I get c3 is equal to 2 c1 over 3. Now remember though, c1 we already said was 0, so this gives us a 0. If I plug in k equals 3, I get c4 is equal to 2 c2 over 4. c2 is above, that's really c0, so we get 1/2 c0. If I plug in k equals 4, I get c5 is equal to 2 c3 over 5. c3 though is 0. So we're going to hope that we start to see a pattern. We're going to keep doing a few more. If I plug in k equals 5, I get c6 is equal to 2 c4 over 6. c4 though is that 1/2, so I really get 1/3 times 1/2 c sub 0, which is 1/6 c0. Okay, if I plug in k equals 6, hopefully you can tell all the odd ones are going to be 0. And then lastly, k equals 7. It's not the last term, it's the last one that we're going to find. We get c8 is equal to 2 c6 over 8, which is 1/4 times 1/6 c sub 0, right, because that's c6 we found down here. So we get 1/24 c sub 0. Okay, and we could keep going. We're hoping to find a pattern of some type. Okay, so let's see where this takes us now. Okay, so let's remember that we said our solution was going to be y equals the sum from n equals 0 to infinity of c of n x to the n. So if we plug in n equals 0, we get c sub 0 x to the 0 plus c1 x to the first plus c2 x squared plus c3 x cubed, etc. Okay, so now what we have to do is we have to start plugging in all these c's that we found above. c0 is just c0. c to the first we found was 0. c2 we found was c0, so we get c0 x squared plus 0. c4, c sub 4 was 1/2 c0. Okay, so what we're going to notice is that we can factor out that c, and we get 1 plus x squared plus 1/2 x to the 4th plus 1/6 x to the 6th, and we keep going. Now ultimately we hope to be able to write this as a power series, so we're going to try to look for some pattern. What you're going to notice is 1/2 is 1 over 2 factorial, 1/6 is 1 over 3 factorial. The last one we got was 1/24. That was 1 over 4 factorial. So this is the summation from n equals 0 to infinity of x to the 2n over n factorial. This is our general solution. General solution is a power series. Now what we'll notice about this is if we move some things around, this is really 1 over n factorial x squared to the n. X to the n over n factorial is e to the x, so that x squared is e to the x squared. So this is a solution that we got before when we solved the problem using separation. So that's the power series method. It's tedious, I will say that, and it's pretty easy to make mistakes, so you have to be very careful. It does involve a lot of the skills that we went over yesterday. So a quick point, and then I want to do another example. What is the power series for cosine of 1/3 x? So we talked about yesterday, or we reviewed yesterday, cosine is n equals 0 to infinity, -1 to the n, x to the 2n over 2n factorial. Okay, so I already alluded to this earlier today. 1/3 x, if compared to cosine of x, you're going to plug that 1/3 x in the space of x. So we get the sum from n equals 0 to infinity of -1 to the n over 2n factorial. In place of x, you put 1/3 x. So that is our power series for cosine of 1/3 x. Okay, so that's one example. I know that this is tough, so I think it would be in our best interest to do another example together. So we're going to do one more. We are going to find a series solution of the equation y double prime plus y is equal to 0. Now, if you want to, it might be a good idea to pause the video and start to try this one on your own. If you don't want to do that, that's fine. We'll go through it together. If at some point you think that you can do the problem, maybe pause and see how you do. Okay, so we're going to start out exactly the same as we did before. We are going to assume that a power series solution does exist in the following form. So then if you remember, the next thing that we did is we're going to have to plug into our differential equation. We have y, we're going to need y double prime. So if we find y prime, we get the sum from n equals 0 to infinity of n c to the n x to the n minus 1. Then if we take the derivative again, we get n quantity n minus 1, c to the n, x to the n minus 2. Okay, as we did before, notice if you plug in 0, you're going to get a term of 0. If you plug in 1, you're going to get a term of 0. So we're going to change this so that it starts at n equals 2, because we don't care about those first terms of 0. Okay, so then what we did is we went back to our differential equation. Second derivative, add y, so we get the sum from n equals 2 to infinity of n minus 1, c to the n, x to the n minus 2, plus n equals 0 to infinity, c to the n, x to the n. Okay, so next thing we did is we looked at what terms each summation starts with. If we plug in 2, we start with x to the 0. If we plug in 0, we start with x to the 0. So that's a good sign. We don't need to change, we don't need to remove any terms like we did in the previous problem. But this is a problem. N equals 2, n equals 0. So if you remember from before, we're going to let k be equal to n minus 2, and we're going to let k be equal to n. So all we're doing is we're replacing n with another variable. It's not going to change the value of the summation at all. So this first summation then, if we plug in 2, we start from k equals 0 to infinity. That n then is k plus 2. So we get k plus 2, k plus 1, c to the k plus 2, x to the k. Here all we're doing is replacing every n with a k. And then hopefully you remember the whole point of doing this was so that we could get one summation together. So we're going to put those two together. We get k plus 2, k plus 1, c to the k plus 2, plus c to the k, x to the k equals 0. The only way this power series is going to equal 0, besides x being 0, which is not very interesting, is if all of these coefficients are equal to 0. Okay, so we're going to set that equal to 0. This is going to give us that recurrence relation. Now remember, we need to solve for this term, not this one. We always want to relate a term to previous terms, not future terms. So this is going to give us c to the k plus 2 is equal to negative c of k over k plus 2, k plus 1. And then from our summation above, k starts at 0. Okay, so that is our recurrence relation. What you're going to do now is you're going to start plugging in values of k. We plug in k equals 0. We get c2 is equal to negative c0 over 2 times 1. If we plug in k equals 1, we're going to get c3 is equal to negative c1 over 3 times 2. I'm going to put the evens on one side, the odds on another side, and you should be able to, in a minute or two, see why I'm doing that. If I plug in k equals 2, I get c4 is equal to negative c2 over 4 times 3. That c2, though, is up above, so that really becomes positive c0 over 4 times 3 times 2 times 1, which is 4 factorial. If I plug in k equals 3, I get c5 is equal to negative c3 over 5 times 4. c3 is above, though, so that becomes positive c1 over 5 factorial. We're going to do 2 more. If we plug in k equals 4, we get c6 is equal to negative c4 over 6 times 5. c4 is above, though, so that becomes negative c0 over 5 factorial. Sorry, not 5 factorial, 6 factorial. And the last one we're going to plug in is k equals 5. We get c7 is equal to negative c5 over 7 times 6. That c5 is above, though, so we get c1 over 7 factorial. Okay, so now we're ready to start plugging in those coefficients and seeing what happens. If we remember, we get c0 plus c1x plus c2x squared plus c cubed x to the third, etc. So we get c0 plus c1x. That c2 is up here. So that's negative c0 over 2 factorial x squared. C cubed is over here, so that's negative c1 over 3 factorial x to the third. And we then get c0 over 4 factorial x to the fourth, plus c1 over 5 factorial x to the fifth. Okay, so what you're going to notice, this one's a little trickier. We have c0s and c1s. So we're going to need to separate those into 2. So we're going to bring together all the terms with a c0 and all the terms with a c1. We get 1 minus x squared over 2 factorial plus x to the fourth over 4 factorial. If I bring together everything with a c1, I get x minus x cubed over 3 factorial plus x to the fifth over 5 factorial, etc. Now those should look familiar. Those are not brand new. You've seen those before. This first summation is the sum from n equals 0 to infinity of -1 to the n over 2n factorial x to the 2n. We then have n equals 0 to infinity of -1 to the n over 2n plus 1 factorial x to the 2n plus 1. So hence in this case we have two solutions. Our first solution is exactly what I wrote above. Our second solution is the other one that I wrote above. So those are our two power series solutions. Like I said, sometimes you'll recognize those, you'll know what functions they describe, sometimes you won't. This first one is cosine of x. Second one is sine of x. Please don't forget those constants. So that's something that's really easy to drop. Now a few questions. First question, why did we get two solutions? Whereas in example 5, we only got one. Well, look at your differential equation. Second order. Second order, you're gonna have two solutions. Example 5 was first order, you're gonna have only one. And then just as a fun reminder, how would we solve this? So this is a throwback to last unit. It's homogeneous, it's linear. So this is one where you would look at that aux equation. We would do m squared plus 1 equals 0. So our m is plus or minus I. So our general solution then would have been c1 cosine of x plus c2 sine of x. That's exactly what we have above, just as the two separate solutions. If we were to combine them, we would get the general solution. Okay, so oftentimes the problems you're going to be solving, you do know an analytic way of solving it, but we do need to practice this power series method. Okay, we have one last note that you're going to need next section. You don't need it in this section, but you do need it next section. We say that a function f is analytic at a point A if it can be represented by a power series in x minus a that has a positive radius of convergence. So like I said, that's not really important to us now, but it is going to be important later. Okay, I know that this stuff is tricky, but if we work together, I think you guys can get through this homework. It is incredibly important that you work on the 6.1 homework. 6.2, we're going to be solving with power series again, and it's going to involve a lot of these same skills that we went through in this video. So please make sure this weekend you give that homework a good try, even if you don't finish it. Please use each other in class as a resource to help each other. Good luck.